In this lesson, we're going to use and identify exponential growth and decay functions, interpret and rewrite exponential growth and decay functions, and solve real-life problems involving exponential growth and decay. Exponential growth occurs when a quantity increases by the same factor over equal intervals of time. A function of the form y equals a times quantity 1 plus r to the power of t, where a is greater than 0 and r is greater than 0, is an exponential function. The final amount is equal to your initial amount times the quantity 1 plus r, which is the growth factor, okay, and then r is just the rate of growth, okay, as a decimal. Okay, you'll often see it as a percentage and need to convert it to a decimal. Okay, and then t is the amount of time. The inaugural attendance of an annual music festival is 150,000. The attendance y increases by 8% each year. Part A. Write an exponential growth function that represents the attendance after t years. Part B. How many people will attend the festival in the 5th year? Round your answer to the nearest 1,000. So first I'm going to write my equation, y equals a times 1 plus r in parentheses to the power of t. Okay, a is the initial value, okay, and r is our percentage increase here, and t is the amount of time here. Okay, so my initial value here is 150,000 because that's how many people attend the festival in the first year. Okay, so I'm going to write y equals 150,000, and then times 1 plus 8% because I'm increasing by 8% each year. Okay, and then this is to the power of t. Okay, well, 1 plus 8%, well, 8% as a decimal is 0.08 plus 1 is going to be 1.08 to the power of t times 150,000. So this is my exponential growth function that represents the attendance after t years. Okay. For part B, it asks how many people will attend the festival in the 5th year. Round your answer to the nearest 1,000. Well, the first year we had 150,000 people attend. Okay, so that's actually going to be when t is equal to 0, because if I do 1.08 to the power of t, okay, well, if this is to the power of 0, then this whole thing goes away and I just get 150,000. So t is really the number of years after my first year. Okay, so in the 5th year, that is 4 years after my first year. So I'm going to plug in 4 for t. Okay, so hold on, I'm going to box this for part A. And now I'm going to plug this in, y equals 150,000 times 1.08 to the 4th power, 4 years after the first festival. Okay, and then I'm going to plug this into a calculator and then round my answer. So I'm typing in 150,000 times 1.08 to the power of 4. Okay, and this gets me 204,073 point blah, 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 blah. Okay, we need to round to the nearest 1,000 here. Okay, so I'm going to go to my 1,000 place, which is 4. Okay, I'm going to go 1 to the right. That's a 0. So I'm going to round down to 204,000. Okay, so this value is about 204,000. Okay, and our word answer is going to be about 204,000 people attend in the 5th year. Okay, and now we're done with this one. Exponential decay occurs when a quantity decreases by the same factor over equal intervals of time. A function of the form y equals a times quantity 1 minus r, all to the power of t, where a is greater than 0 and 0 is less than r is less than 1, is an exponential decay function. Okay, so this looks very similar to our exponential growth function, but this time I'm subtracting my percentage because I'm decreasing my value instead of adding my percentage, which would increase my value. Okay, and notice r has to be in between 0 and 1, so r is going to be a decimal. So in this case, we see that r is our rate of decay instead of our rate of growth. Okay, this is the decay factor instead of our growth factor, and then everything else is the same. For exponential growth, the value inside the parentheses is greater than 1 because r is added to 1. For exponential decay, the value inside the parentheses is less than 1 because r is subtracted from 1. Determine whether the table represents an exponential growth function, exponential decay function, or neither. Okay? Well, in this case, I'm adding 1 to x each time. And then if you see here, I'm actually dividing by 3 each time for y. Okay? So since I'm dividing here, or multiplying by 1/3 is that 1/3 is a number that's in between 0 and 1. So since I'm multiplying by 1/3 here, or dividing by 3 in this case, I know that this is going to be an exponential decay function. Okay? For part B, if we see this, I'm adding 1 each time for x. Okay? And as I add 1 each time for x, let's see what's happening for y. Okay, I'm going from 5 to 10 to 20 to 40. I'm multiplying by 2 here, okay? So this is going to be an exponential growth function because I'm multiplying by a number that is greater than 1 each time. So this is going to be exponential growth. And now we're done with this one. For example 3, we're going to determine whether each function represents exponential growth or exponential decay. And then we're going to identify the percent rate of change. Okay. Well, this is actually pretty easy to tell right away because I just need to see what the number that is being taken to the power of t is. If it's greater than 1, it's going to be growth. And if it's less than 1, or what I should say is in between 0 and 1, it's going to be decay. Okay. So right away, I see that this number, 1.07, is larger than 1. So I know that this is going to be exponential growth. Okay. And then to figure out the percentage rate of change, all I have to do is this number minus 1. Okay, so 1.07 minus 1 equals 0.07. And as a percent, 0.07 is just 7%. So my percent rate of change is 7% here. So this is an exponential growth function with a percent rate of change of 7%. For part B, I can tell that this is going to be exponential decay because this number 0.98 is in between 1 and 0. Okay. And then to figure out the rate of change for exponential decay, you could do this number minus 1. You'd get a negative number. The negative would tell you that it's exponential decay. Or you could just do 1 minus 0.98, which is going to give you 0.02, okay, which is 2%. So this function is decreasing by 2% for every unit of t here. Okay? So this is an exponential decay function with a rate of 2%, and then this one's an exponential growth function with a rate of 7%. And now we're done with this one. For example 4, we're going to rewrite each function to determine whether it represents exponential growth or exponential decay. So remember, I can rewrite this fractional exponent here for part A, y equals 100 times 0.96 to the t over 4 power. I'm going to zoom in here for a second. So I can rewrite this as y equals 100 times 0.96. And I'm going to break this fraction up. I'm going to have this be to the 1/4 power. Okay, and I'm going to erase my parentheses here for a second. So I'm going to have this be to the 1/4 power, and then I'm going to have this all be to the power of t. All I've done is I've broken up my fraction using my exponent properties here. Okay. So now what I can do is I can take the 4th root, or take 0.96 to the 1/4 power, okay, and then I'll be able to tell if it's exponential growth or exponential decay. Okay, so I'm going to rewrite this as y equals 100 times, okay, and now I'm going to go to my calculator to do 0.96 to the 1/4 power. So 0.96 to the 1/4 power, remember that's the same thing as taking the 4th root, both will work. Okay, and I get 0.9898 blah, 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 blah. So this is, I'm just going to round this to, let's say, 0.99. Okay, this is about 0.99 to the power of t. Okay, so even after I've calculated this, I know that this number is still in between 0 and 1. So this is going to be exponential decay. So I'm just going to write decay here. Okay, so now we're done with part A. So for part B, I'm just going to rewrite this using my exponent properties. I'm going to rewrite this as f of t equals, and then I'm just going to break this up. Okay, I'm going to break this up into 1.1 to the t times 1.1 to the negative 3. Remember, if I multiply the bases, I just add the exponents. In this case, it's t plus -3 or t minus 3. Okay, and I can also just rewrite this on the bottom of the fraction with a positive exponent. So this is going to be f of t equals 1.1 to the t over 1.1 to the positive third power. Well, I'm going to do 1.1 to the third power out just to simplify this fraction. So I get 1.1 to the third power, and this gives me 1.331. Okay, so I get f of t equals 1.1 to the t over 1.331. Okay, but now I'm actually going to write this as a fraction here, being multiplied by my number being taken to an exponent here. Okay, so I'm going to rewrite this as f of t equals 1 over 1.331. This is definitely not simplified because there's a decimal in it, but for our purposes, this is fine because now I'm multiplying this number by 1.1 to the t, and I know, even after I've rewritten this, that this is still going to be exponential growth because the number that's being taken to a power is greater than 1. So this is going to be exponential growth. And now we're done with this one. Exponential growth functions are used in real-life situations involving compound interest. Although interest earned is expressed as an annual rate, the interest is usually compounded more frequently than once per year. So the formula y equals a times 1 plus r all to the power of t must be modified for compound interest problems. Compound interest is the interest earned on the principal and on previously earned interest. The balance y of an account earning compound interest is y equals p times quantity 1 plus r over n to the nt power. Okay, where p is the principal or the initial amount, r is the annual interest rate in decimal form, t is the number of years, and n is the number of times that interest is compounded per year. Okay, so all I've done to get this equation is I've taken this equation, which is you could think of as yearly if it happened once a year, if the interest was compounded one time per year. Okay, but I basically broke that up into however many times per year. So if it was monthly, I would do n would equal 12. Okay, so I'm dividing the rate by 12 here. Okay, but I'm doing that 12 times per year instead of once per year. Okay, if it was daily, then n would be 365 or 366, depending if it was a leap year, but you would multiply that 365 or 366 times per year. Okay, so that's how we get this compound interest formula. For example 5, you deposit $100 in a savings account that earns 6% annual interest compounded monthly. Write a function that represents the balance after t years. Okay, well, first I'm just going to write my general compound interest equation. Okay, so that's going to be y equals p times 1 plus r over n to the nt power. Okay, so now my initial amount, $100, well, that's going to be my principal investment. So I'm going to plug that in for p. Okay, and then 1 plus r over n. Okay, well, my rate is 6%, so that's 0.06 as a decimal. And then over, okay, well, how many times is this interest going to be compounded over the year? Well, it's monthly. There's 12 months in a year, so that means my n value is going to be 12. The number of times is 12 because it's monthly. Okay, and then over here, I have to plug in 12 again for n, and then t is the number of years. Okay, and we're just going to leave it like that. So t, I'm going to bring down my y equals. Okay, and now all I got to do is simplify this. Okay, so I can simplify 0.06 over 12. Well, I know 6 over 12 is 0.5, but the decimals moved twice, so I can move it back over. So it's going to be 0.005. And then if I add 1 to it, I can change this 0 to a 1. So this is the number that's going to be multiplied repeatedly, okay? And then this will be taken to the 12t power times 100. So that right here is going to be my compound interest formula. So however many years I leave it in the account, I can just plug that in for t, and then the total value, that will be how much I have after that certain amount of time period for this given rate with the monthly compound interest. And now we're done with this one. For example 6, the table shows the balance of a money market account over time. Part A, write a function that represents the balance after t years. Okay? And then part B, we're going to graph the functions from part A and from example 5 in the same coordinate plane. Compare the account balances. All right, so first we need to figure out what function we have here. Okay? Well, 0 years means that no interests have been compounded here. Okay, so this is going to be 100. So my principal amount here is going to be 100. So I'm going to write that down. P equals $100. Okay, and then if you notice, each time here, I'm increasing my previous value by 10%. Okay, so to get from 100 to 110, I can multiply by 1.1, and which is the same thing as a 10% increase. Okay, and then to get from 110 to 121, I still multiply by 1.1, and so on. That's what I'm doing each time. Okay, so my growth factor is going to be 1.1. Okay, which means I have a 10% increase. So this is going to be, so R will be 10%. Okay, and this looks like it's just a yearly. So my equation is going to be y equals 100 times 1.1. Okay, that's my 1 plus 10%. To the power of t. Okay, so that is the equation here. If you remember, my equation from the last example was y equals 100 times 1.005 to the 12t. Okay, so I'm going to graph both of these equations for part B, and then we're going to compare them. Okay, so for the first one, our table is actually given to us already, so I don't even need to make a table because I already have one here. Okay, so I'm going to scroll down. So if you remember, my first value was 0 years, I had $100. And then after 1 year, I had $110, so that's going to be somewhere right there. And then my second year, I had $121. My third year, if you can see right here, I have $133. Okay, and my fourth year I have 146. You're right there. I'm actually going to fix this point right here. Something like that. Okay, and then my fifth year I have $161. It's going to be like that. Okay, so you can see that it's a slightly exponential curve right now, but as we increase, our value is starting to grow at a faster and faster rate. Okay, so I'm going to just draw a sketch through that. So something like that for my first one. Okay, and then here, what I'm going to do is I will make a table of values here based on this equation so I can plot. Okay. So I'm actually on Desmos graphing calculator right now, and I'm just going to type my function here, which is going to be 100 times 1.005 to the 12 and then x1, and then this will allow me to easily make a table. You can do this out by hand or by a calculator, but this is a quick, easy way to do it. Okay, so I have 100, 106, 112, or 113 I should say, 120, 127, 138, 143, and 152. So I'm just going to plot those right now. I'll do that in red. So 0, 100, same spot. Then I have 1, 106, just a little lower. Okay, and then I have, I'm going to zoom in on this to make it a little bit more accurate. Then I have 1 or 2, 113-ish. It's about halfway there. Then I have 3, 120. Which will be something like this. Then I have 4, 127. Okay, then I have 5, 135-ish. Then I have 6, 143. And then 7, which goes with 152. Okay, so this is also an exponential curve But you can see that even though I'm compounding every month as opposed to every year, that 10% annual rate is still going to grow at a faster rate than the 6% rate compounded monthly. Anyway, we have successfully graphed and compared our account balances for both of these equations, and now we're done with this one. For this example, the value of a car is $21,500. It loses 12% of its value every year. Part A, write a function that represents the value y in dollars of the car after t years. Part B, find and approximate the monthly percent decrease in value. And part C, graph the function from part A, use the graph to estimate the value of the car after 6 years. All right, well, this is an exponential decay question because we know that we're losing 12% of the value every year. Okay, well, to figure that out, I'm going to write my equation, which is going to be y equals 21,500 times 1 minus 12% to the power of t. Well, 1 minus 12%, you can kind of do that in your head pretty quickly. It's going to be 0.88, okay, to the power of t times 21,500. So this is part A. We've successfully written our function. Part B is asking us to approximate the monthly percent decrease in value. Okay, this is a little bit tricky. Okay, we need to use a bit of clever math in order to figure this out. Okay, so I'm going to take this function. I'm going to rewrite it over here. So this is going to be y equals 21,500 times 0.88 to the power of t. Okay, but I want a monthly percentage here. Remember, t, this is representing the amount of years. Okay, well, I know that there's 12 months in a year. So the way I'm going to do this is I'm actually going to rewrite this as y equals 21,500 times 0.88 to the power of 1/12 times 12t. Okay? Remember, for compound interest, in order to have monthly compounding interest, I would have 12 being multiplied by the number of years because it would happen 12 times per year. Okay? Well, to do the same thing, I'm going to do that, but in order to keep this the same value as t, I need to multiply this by 1/12. Okay? And now I'm going to use my exponent properties to rewrite this as y equals 21,500 times 0.88 to the power of 1/12 to the 12t. Okay, so now all I need to do is simplify this, and then we'll get our monthly estimation of our decay rate. So I'm going to plug 0.88 into the calculator. So 0.88 to the power of 1/12, aka the 12th root of that. Okay, and then if you see right here, I get 0.989. Okay, and I'll leave it as 3 decimals. Okay, but because we're just rounding here anyway. So 0.989. So if I go back here, I'm going to rewrite this as y equals 21,500 times 0.989 to the 12t power. Okay, so remember, this 12t allows us to calculate this monthly. And you could do this for a different number. Here, we just break our fraction up. Like, let's say we did quarterly, 4 times a year. I'd do 4t and then 1/4 here. Okay, so it doesn't matter how many times you do it per year. Okay, but this is just how to do it monthly. Anyway, I want to go back up and see what my question is actually asking. It says, find the approximate monthly percent decrease in value. Okay, so now I know that this is exponential decay, so I'm going to do 1 minus this number. Okay, so 1 minus 0.989 to figure out the percentage decrease here. So this is going to give me 0.011. If I move the decimal over twice, I get 1.1%. So for part B, the value of the car is decreasing by about 1.1% each month. Okay, so now we're done with part B. So let's go over to part C. So part C says graph the function from part A, use the value of the graph to estimate the value of the car after 6 years. Okay, well, whenever I'm graphing and feeling unable, I like to make a table. So I'm going to make a table of values here. And I'm actually going to go use the Desmos calculator because it's going to save me time. So in this case, I'm going to change this. And it says use the graph to estimate. So I'll just go up to 5, and then we'll use our graph to estimate. But you could plug in 6 and see what the value would actually be. So it's going to be 21,500 times 0.88. And then I'm going to do to the x1 again. Okay, so I get these as my values. So I'm going to plot these numbers on my graph right now. So 0, 21,500. Then I have 1, about 19,000. So that'll be somewhere right there. Then I have 2, about 16,500. So somewhere like there. Okay, and then I have 3, which is about 14,500. Something like this. And then 4 will give me a little less than 13,000. So like that. And then 5 gives me a little over 11,000. Something like that. Okay, so I'm going to fix this point right here. Okay, I'm going to sketch my graph here. So something like this. I just like to sketch it. Once again, you can try to draw a smooth curve through there. Anyway, I'm going to go to 6 right here. And after 6 years, it looks like it's just going to be around $10,000. So that's going to be my approximation. So about $10,000 after 6 years. Okay. And I'm actually going to go to the table of values that we made in Desmos and see how accurate my guess was based on my graph. Okay. So if I go here and type in 6, it's 9,984. So we were pretty close. We're only off by about $15 or $16 here. So anyway, we've successfully graphed this equation, we've successfully figured out the monthly percentage, and we've successfully written the function. So now we're done.